Log on, tune in, find out. Another good idea from Cambridge.
Our next speaker is Hermann Held. And he's going to talk about climate investment. So over to Wesley.
Yeah, thanks a lot. Thanks for inviting me into this prestigious seminar series. And I'm happy to announce that I can also celebrate the 100-year start of my grandfather his study here in Cambridge. So we then had to live in an English garden afterwards as a family, but it was a pleasure actually. So I moved to the Klima Campus Hamburg. This is the outer shell of a cluster of excellence on climate in Germany, and actually it's the only one that we have on a national basis. So this is a cluster made up by the Max Planck Institute of Meteorology and some university institutes and also some additional institutes. I also stay with PIC. I have been working at PIC for 11 years and got addicted to it to a certain extent. So I couldn't completely leave, and we will form, I think, a coalition in the future. Now, I will briefly introduce the term climate problem as the climate economists see it, and then would like to focus on the cost-effectiveness analysis of optimal energy investments. And energy means mainly mitigation, so transforming the energy sector. So I discussed this with the organizers of this workshop, and they said, well, it's okay if you also give some notes on mitigation, because on the one hand, this frames the need for adaptation. The more we mitigate, the less we need to invest for adaptation. On the other hand, most of the methods would also apply in the economic analysis of adaptation measures. And finally, I would like to introduce the concept of uncertainty in these economic investigations that haven't been injected most of the time of the climate discourse yet. Now, the so-called climate problem. Why do we, or not we, but why may a society want to mitigate? And it seems that there are two streams of argument. One goes along the explicitly known damages, sort of projected by climate models and then successively impact models. So this is what you positively know. And on the other hand, you have the precautionary principle that refers to effects that you don't know. So we would not like to transgress certain limits because we do not know really what would happen then. And the EU at least made the precautionary principle a very important principle, at least officially, for their policy. So this was claimed in 2000 and later on again in very general terms, not only for the climate issue. So here are two streams of argument, and the 2-degree target can be seen as a convolute of these two lines of argument. And one argument along the precautionary principle goes as follows. This is the way I read it, that you ask yourself, what is the dangerous global warming? And as a physicist by training, I would like to see a scale on temperature, and one scale is given by the temperature difference between Holocene and the last ice age. So this is roughly 4 to 6 degrees Celsius. And therefore, one may say this was a big effect, the switch between the Holocene and the last ice age. And on the other hand, if we asked ourselves if we went for the same amplitude just to the positive side, then we would end up in a hothouse in a temperature range that we haven't seen for roughly 50 million years. And therefore, one may want to engage the precautionary principle here to stay away at least more than 50% from this difference in amplitude. So this could be one out of many arguments that are supporting at present the 2-degree target. It could also support a 1.5-degree target, of course. So this is at least one example for this second stream of argument, and one school in economics is taking this up. This is why I'm mentioning it. Now there is one category of impacts that may be allocated at the borderline of the two streams of argument, so these so-called tipping elements. And you may say this, the knowledge on the fact that we have tipping elements in the Earth system may support the concept of a precautionary principle. If we do not know too well about the location impact of these tipping elements. And on the other hand, if you have accumulated the knowledge on the impacts of triggered tipping elements, then of course you are more on the positive knowledge side on this first category. Now I see the 2-degree target as a convolute of the two, and in the remainder of the talk we would assume that policymakers are interested in an analysis of the 2-degree target, the effects of the 2-degree target. If it was implemented, what would it mean? And this is what this second part of the talk does, a major part. And in terms of emissions, I would like to define the so-called mitigation gap. So this is the difference over time between a business as usual scenario and an emission path that would be somehow in line with the 2-degree target. In essence, it's a 50% chance to observe the 2-degree target if you followed this green line. You see that the mitigation gap is widening along the timeline, and this is why mitigation, and especially the 2-degree target, is so ambitious from political point of view. And many climate economists in the past claimed they to have made a welfare analysis, welfare optimization analysis, and as a result of the analysis, the recommendation was given that you would start to mitigate on a massive basis just in the middle of the century. So this was supposed to be socially optimal, and this recommendation was very influential. Now the Potsdam Institute also looked into this. I would like to give you some key arguments of this reasoning. This so-called cost-benefit analysis that is usually done in economics is following a very simple logic. So you make up an equation. The gain from climate policy can be separated into the avoided damages on the one hand through mitigation, and on the other hand the mitigation costs you have to come up with, and also adaptation costs, of course. Now this is a very quick and dirty statement. All the intertemporal effects are not mentioned here, so you have to have a cleaner concept if you want to discuss the climate problem. So the reasoning is again quite simple. You have a socio-economic system that emits because you want to create further welfare, and in fact we expect a rise in energy demand by a factor 3 to 5 during this century. So if this stays coupled to the use of fossil fuels without carbon capture and storage, then in fact we would face further emission increases, as I had shown before, that would act on the climate system, and we would have a feedback of the climate system on the socio-economic system in terms of impacts. Now this difference between avoided damages and mitigation adaptation cost, this is called, or in a more exact way, this is viewed as a utility, so the happiness per generation. And the happiness per generation should be summed up, should be integrated from now unto infinity and discounted to a certain extent, because you do not know whether you live tomorrow, or even you could say the fact that I observe an interest rate that shows that somehow the future is not so important to people than the present day situation. So if I lend someone money, I want more back in the future, because it's very painful for me to give away the money now and to get something back in the future. In turn, you have to add something to that to make it attractive to me. Now, in principle, this functional could be optimized if you had all the mechanistic information from the cycle, from science, going into this utility function. And for an economist, utility moves up with consumption, basically, and then you just optimize it in a numerical model. Now, with this approach, you face a couple of very deep conceptual problems. On the one hand, the impacts are very poorly known, and that might not change over the next 10 years. So here you have a massively underdetermined problem, and therefore the question is how you treat all the impacts that you do not know, and very often the impacts were treated by setting them to zero, those impacts that you don't know really. Especially those impacts that could massively harm an economy on a very persistent way, so that the impacts in the long run are rather large, and very often economic models are not able to map this. On top of that, simply many impact chains are not known and they are just not treated. And on the other hand, you have to weigh in present mitigation costs against future avoided damages. So the question is, how do you discount the future? And I just mentioned that this exponential discounting is something that in principle has to be set. The question is it a normative parameter or is it a descriptive parameter? And if you derive it from the interest rate, it is interpreted as a descriptive parameter, whereas Lord Stern interprets it as a normative parameter. So it should be almost 1, this factor that discounts, he says, because it would be unfair to discount the future too much. If he took the interest rate, then basically the generation in 100 years is discounted such that it weighs only in at maximum to 30% or so, or even less. So this is a quite a difficult concept. Now the question is, are there other concepts around? And in fact, this is a concept the Potsdam Institute employed over the last years, I would say since the year 2001. And the idea is that you chop off the damage part. You replace it by the political goal, let's say a 2-degree target, and ask only for the costs, so how to minimize the costs of mitigation. You talk only about mitigation. And then you do not get rid of totally this problem of discounting, but you know the switches in the energy sector, they are now. You don't have to trade them off against avoided damages in 100 years. So while this factor, which is a bit critical, this normative or descriptive factor, is still there, it's not so influential anymore. And you have avoided all this ill-postedness in the damage functions. So we claim that we know much better on the energy sector costs than on the damages. So this is at the heart of such a modeling approach. On the one hand, you have to have a climate model, at least a module, a very primitive climate model, an emulator, if you like. So we use sort of an energy balance model, and these days we use a version that is equivalent to Magic C. You need an energy system model and you need an economic growth model. A model that maps the fact that economies like to grow, that they have grown in the past, and from these models you can then deduce what the consumption losses would be, and the logic within such an economic model is in essence quite simple. You produce in this economy, and part of what you produce per year can be either consumed or reinvested into further capital, labor or energy. These are the very crudely resolved production factors. So capital here means not only money but all the factories that produce. Yeah? So this is a capital stock that you may build up further from the output in order to produce even more in the future. So this is an interesting debate in its own, even without the climate problem. How much should a society consume and how much should it reinvest? So this is from the point of view of the whole society, not of the government and not of a factory, but as a very macroeconomic point of view. So such a module is being used. And in fact, with such a module, if you run this optimization, you can understand the economic growth in the past. So if you like, these are the Newton equations of economy. They are not formulated as differential equations, they are formulated in terms of an optimization that seems to me has some descriptive power. Otherwise, these models would be useless. So they must have some kernel that has a meaning objectively. And to me, that seems to be the case, in fact. Now we take this model and run it and put now a target on it. So the climate model would say us how much CO2 we have to save in order to stay below 2 degrees, and otherwise this economic optimization, the optimization is run, and the model would enforce so many renewable powers or other energy options as to reduce the CO2 emissions, and nevertheless keep up the economic well-being. And this mitigation gap that I've shown you before this is now filled up with a set of technologies that are enabled in this model. So you have nuclear power, you have renewables, you have biomass plus CCS and without, you have fossil fuels with and without CCS, and you have energy efficiency. Energy efficiency is a mix of cranking up the efficiency of power plants on the one hand and isolation of buildings on the other hand. Now this model has been improved, so the energy sector is resolved better and better, and one of the results is that gas, in fact, is one of the only options that would be enabled in the future even without carbon capture and storage, whereas coal is phased out. Coal without CCS doesn't make sense economically anymore under a 2-degree target. In fact, the economists don't like these temperature targets because then they need a climate model. So what they usually use instead is a concentration target. But for these purposes here, this is sort of equivalent. Not for you, of course, but now we try to push also for the 2-degree or other temperature targets in these calculations. Now the key result of the second part of the talk is displayed. The question is always, what does it cost at the end? Yeah, I mean that we can replace all these dirty technologies by others. This is known for some time. You can do it, especially if you are willing to pool energy sources. So if you want to be sort of self-sufficient on a national basis, then it's not so easy. That basically means that you have to go to nuclear on a massive amount, or to a massive amount to CCS. Whereas if you pool the energy sources over Europe, for example, so if you are willing to harvest the renewable sources in the summer in the Mediterranean and in winter times the wind, then it's much more convenient, in fact. Now, first of all, I would like you to focus on this violet bars here. These bars, and here we display a model intercomparison, the comparison of these integrated models. So these communities sort of learned from the intercomparisons in the climate and the carbon cycle sector. So we always told economists, you have to do this, otherwise people wouldn't listen, especially if you go into policy advice with it. What we plot here is then the consumption loss. So the consumption loss is a measure for the loss of the welfare of the society. So in the end, it's not the production that it's important, it's the consumption for the happiness of people. And therefore, the consumption loss is displayed here, and it's roughly 1%. Yeah? One model says it's much less, another model says it's 1.5%, but it's roughly 1% of the standard consumption aggregated over the century that you would observe. And now the question is, for a natural scientist, is this a large or a small number? 1% sounds very small, but you have to know the field in order to judge. And I learned, and it's hard to find it and somewhere pinned down, but it seems that 0.5 to 1% is a small number for most of these macroeconomists. And on the other hand, 20% seems to be a worldwide crisis of the economy, and 5% is a number where politicians get nervous. If you have a cost of 5% or a consumption loss of 5%, then politicians become extremely reluctant to implement a measure. Therefore, it was a very important result that the costs of the 2-degree target are rather minor. Yeah, below 1%, or some say 2%, but this seems to sort of be the average number. So 1% is the scale, what we are talking about, and these results in part entered also the Stern report in 2006 and 2007, and these are much more refined results these days, but the order of magnitude stays the same. So in that sense, one can say, in principle, the 2-degree target is not too costly, and we could stop here. So if society was saying, in fact, that the precautionary principle is so important for them that they would like to comply with it, if it's not too costly, then the discussion is over. Yeah, we could start to implement it. But there are actors worldwide who want to know more. They want to know more why we want mitigation. We want much more information on the impacts. But this would be one way to stop the analytical discussion. There's a side product of this analysis. You could ask, if I froze one or the other technology for political reasons, you know that in Germany nuclear is very much debated. It's not trivial that the German society will upgrade nuclear in the future. Most likely it will be phased out. And therefore, as an economist, one can always ask what are the additional costs if you are working in a more rigid environment where you are not having this additional degree of freedom of nuclear, for example. So you always know that the cost must be larger because one degree of freedom is missing, and therefore the optimization is constrained to a smaller dimension in space. So the key message is that you have a ranking between technologies in terms of the extra costs that you would induce by not using them. And you see that the nuclear option does not induce too much additional costs. It's only 0.1%. In that sense, we can say among this clustering here, the nuclear option is the option we could get, we could afford not to use too much in the future easiest. Yeah? Whereas the renewables are the source which is hard to not to use if you want to comply with the 2-degree target. And other options are ranked in between. Now, what does it mean? How much does society have to invest? And the key result is here. So under the climate target, this is something equivalent here, not a 2-degree target, but 450 ppm target. You see the lion's share goes into the renewable sector. So between half and 1% of GDP per year. And at the moment we are investing worldwide, these are always worldwide numbers, 0.1 to 0.2% of GDP. So according to this calculation, if you wanted to reach the economically optimal path, and path means time series, you had to crank up the investment into renewables by a factor 3 to 5 roughly. So this is the scale we are talking about. Okay, so all of this was in a world of perfect foresight, no uncertainty, so the topic would be missed by this talk. At least you learn here that there's a certain regime shift now among climate economists, that there's a growing group of people who say that the 2-degree target might not be too costly, in fact. So there's some certain maneuvering space now for mitigation. And therefore, I would say after this now is more and more consolidated, the probability that we in fact will stabilize one day, given the enormous amount of further damages that we will observe and that will be translated by the media in a superlinear way, the probability is very high that at one day, in my view, this is now an informed guess, this is not a scientific statement, we will have some mitigation treaty, something like this. And therefore, I think the probability that you only have to adapt for 2 to 3 degrees has grown as against the probability to have to adapt to 4 to 6 degree world. Now, how does all this play out under uncertainty? The problem for society is, of course, they have to invest under uncertainty, like any company does. And therefore, it's important to have an analysis that absorbs this uncertainty in the concepts. Because if you invest too early, you have sunk capital. If you invest too late, you may have triggered undesirable effects, and then it's too late. So there is sort of room for optimization. In that sense, again, it should be part of such a welfare optimization, but this welfare optimization must explicitly represent uncertainty. Now we use not the Riemann model for this, but a simpler version. So in essence, the energy sector is not so drastically resolved. We have only a very primitive sector of 3 major technologies. And we allow for the uncertainty, of course, in climate sensitivity, because I worked on it in the past, and it's an important parameter, property, I should say. It is a parameter in our simple model. It's an important property of the climate system of GCMs. But we also allowed for uncertainty in the ocean heat uptake, and we did this in a sort of correlated way. I will describe the next slide in the little climate module. And I searched around in the literature. The the IPCC report did not give too much information on the on the joint probability density function of these two parameters, and I sort of converted a work by Dave Frame et al. From 2005, where they in fact give a correlated information into this graph. So this is the ensemble we are using numerically. So all of this is done numerically, of course. You have to optimize basically a 500-dimensional space in the deterministic situation, because you have all the time slices of 5 years and you have many, many streams of investment. And on top of that, you get uncertainty. So this is the ensemble we use. So this should sort of span or mimic the probability density functions in this two-dimensional space. I suppressed the discussion of the cipher forcing uncertainty. So cipher is emitted in the model coupled to coal-fired power plants, and then cipher is gradually phased out, so exponentially phased out during the century. But we suppressed in this more, let's say, technical and conceptual paper, we suppressed this discussion. So we also have uncertainty in the economic sector, especially on the fossil resource base, and also of the so-called learning rate of renewables. So this is the lowering of costs by building more power plants. This is a very important parameter. It's not the only one, but it's a very important effect. And this might not be properly represented in many economic analyses. So we have 10 by 10 by 300 representations. So we have in principle 30,000 parallel worlds, but this matrix is not completely filled because you have a little decoupling here and there in equations, but in principle you can think of such a Monte Carlo experiment. So first of all, we did some sensitivity studies before we do a very difficult numerical optimization including uncertainty. We first want to know what are the effects of the different parameters. It's always the first very primitive thing that you do as a scientist. What are the crucial effects? What are the orders of magnitude of my uncertainties in the different parameters? Now, climate sensitivity is pronounced here in the way that I asked for the economic loss, so consumption loss, for example, as a function of climate sensitivity across this 30,000 ensemble, member ensemble. And you can see that there is, in fact, a high correlation between the two. Climate sensitivity is an important parameter, in fact. It is not the only one, but it explains much of the uncertainty in climate prediction. So I would say between a half and 70% or so. And you see that, in fact, there is a certain slope, cost versus climate sensitivity. That must be the case. The larger the climate sensitivity, the more we have to save in terms of carbon to observe the 2-degree table, and the more costly it gets. This is not surprising. We can determine the slope of this, and this gives you the feeling what is the importance of climate sensitivity in knowledge in economic terms. So if we could prove that we can lower the upper bound of climate sensitivity by 1 degree Celsius, we can save 0.5% of GDP, up to 0.5% of GDP, according to this very optimistic model in terms of mitigation costs. There are other models around that claim higher costs. We would save then even more. So this gives you a first feeling of the economic value of information on climate sensitivity. This is sort of the maximum. This is an ex post reasoning if we had observed that. Now, as you know, I also did some work on climate sensitivity before. And these were the error bars until 2005 from all these EMIC experiments, and they went up to roughly 10 degree. And the idea was to have an additional system or approach by which you sort of tap another source of data from from the Paleo scale, so from the last glacier maximum. So this was work by my PhD student Thomas Schneider von Daimling. Some of you know him. And we back constrained in the world of our Climber 2 model, one has to say, not with the GCM, the error bars, and these are now 5 to 95% quantiles. These are not the IPCC quantiles of 66%. So this is a much more important information. So we back constrained it to roughly 2 to 4.5 or 5 degrees. And we played with these numbers then in the economic analysis, just to emphasize again, if I have a scheme that relates paleo information somehow to an economic metric. There must be a way to give this paleo information an economic value. And if I talk about percent or at least tenths of percent of GDP, I'm talking about very, very large numbers. GDP, worldwide GDP is between 50 and 100 trillion US dollars. And I think that paleo research does not get that scale. So this could be a mechanism to, from purely rational grounds, argue against, so in the context of politics, that this part of research should receive more funding. So by orders of magnitude at least. Yeah. So this is the point I want to make here. Now we go more into the techniques of this analysis. The influence of climate sensitivity on the optimal emission path, an economically optimal emission path, is dramatic. All of these can't be excluded from scientific reasons, so this is a climate sensitivity change from 2 to 6 degrees, and you basically can produce any emission path that you like. So there is no point to make a sensitivity study anymore. So it is completely underdetermined. This is the point. You have to absorb the uncertainty in the economic optimization concept. It's not enough just to do a little twiggling afterwards, after you have done the optimization. So what we do is we replace the utility optimization or welfare optimization by an expected welfare or utility optimization. And then, if you allow for uncertainty in the link between CO2 emissions and temperature, then of course the probability to observe the 2-degree target must be specified. 100% is not possible. We know this because of the tails of the climate sensitivity distribution. Many economists publish under the assumption there is no tail, so they chop off with 4 degrees or so. So it is in fact a probability statement that is needed in addition to the target. Otherwise, it's not a well-posed research question. Now this chance constraint, as it's called in economics, is still not properly defined. We need another decision. So suppose you have a system where you have an ensemble of 2 members, one temperature path and another one. Is now, in this example, the probability to observe the target 50% or 0. You could argue per time slice, my probability is 50%, here it's 100%, here it's again a 50%. But you could also say none of the paths would fulfill the 2-degree target. Yeah. So the probability is 0. This is a stricter version of the chance constraint, and this is what we decided for. If we have a tipping point in mind, it doesn't matter when it's triggered. It's very hard to bring it back by definition, and therefore you should not trigger it at all. So this is the idea behind this stricter definition. So this is what we implemented numerically. So what you do in this economic model is, this is what you do in the deterministic way. You optimize, and the temperature path is numerically kept below 2 degrees, whereas now you keep a certain percentage, 75%, for example, of all ensemble members below the 2-degree target. The others are allowed to overshoot, and this is the reality. You cannot observe a temperature target with certainty, and you have then to specify the probability density functions in the end. Yeah, otherwise this can't be done. This calculation, you see the collection from the IPCC report. In colored, and this is the sort of the emulation of the frame paper that we did. It's a very conservative emulation, so we sort of we cover a very broad range. But if we also allow for the additional information from the Schneider and von Deimling et al. Paper, then we get a much sharper distribution. In fact, we get a Gaussian. So this is a very important aspect of this paper, that you get rid of the fat tail. This is what we think, what makes this paleo data so interesting. And this is just the most pessimistic version. There are other interpretations of that paper that would shift the black fat curve even to the left. So we worked with this black fat curve, and this is the first result. These are now the optimal futures over the ensemble. So these are the economic losses as again per time slice against the business as usual path, and you see the losses peak somewhere in the next decade. So it's our generation that has to pay for this stuff if we want to go for the 2-degree target. Later on, we may even have a benefit in case we find that the fossil resources were smaller than we thought on average. But the costs are still clustering around a value that is sort of not so large. And this is the optimal solution in terms of investments into the renewable sector. I picked the renewable ones because they were supposed to be the most important ones in terms of absolute investments. So this is the optimal path for the deterministic model with the standard tunings. So the threshold would be in the mid of the century. And you shouldn't take these numbers too literally. It's a very simple version of the economic model. Whereas in the fully probabilistic equation, you have a much earlier crank up of the investments. So it's roughly 20 to 30 years earlier that you have to invest. You may say, okay, that's trivial. If you ask now for 75%, and before you had worked with the average values, for example, of climate sensitivity, which it might be equivalent roughly to a 50% target, it's not surprising at all that you have to invest earlier into clean technology. But this explains only part of this shift. So we then emulated the 75% target with a sort of artificially cranked up climate sensitivity to 3.6 degrees, so which was taken from the probability density function. So we asked for that quantile. And then you would get this thin but dashed curves. And then, and we further tuned the ocean parameter. We went away from this probabilistic statement and had three versions. And the model picks the most extreme ones. So it's not on the average path, it's on the extreme ones, especially here. Sorry, this was not for ocean, this was for the technology parameter. It goes to the extremist version that we had plotted here. So there's something in addition going on, some nonlinearity in the system we don't understand yet. So this paper is just seen as a technical study. This is still not the decision problem the society has to solve, because society knows it will learn further. It will learn about climate sensitivity, and this was Miles Allen's claim in 2007, give up the quest for climate sensitivity. The question is this true? This is a very clever thought. If climate sensitivity is very large, the system is slow, and I can learn further in the future and then switch to renewables. So this was a trigger to set up a model environment where you can really also account for the learning effect. So in the previous setup, we don't learn at all. There's a probability density function from the beginning. I have to invest, and I cannot change my course of action. Whereas here, we allow for the fact that society will observe, and it's still ongoing. And we observed a very nasty conceptual effect first. So this was implemented. This was the path I've shown before here now in terms of CO2 emissions. So from this chance-constrained program without learning, if we know and we allow here for three futures of climate sensitivity, it's basically 1.5, 3, and 4.5 degree with a certain width, a reduced width after learning. So we learn in 2030. If this is the case, if I know from the beginning, I may learn that the climate sensitivity is in fact 4.5, I have to reduce my emissions much more from the beginning. I have to prepare for the worst case. And this already shows that the whole concept might be a bit shaky. So if I don't go for this very artificial situation where I chop off at 4.5, but I know that I allow for the fact that the climate sensitivity could also have larger values, that I may run into situations where I learn that climate sensitivity is 6 degrees, and then I cannot observe the chance constraint anymore. It's impossible to stay with a certainty of 75% below 2 degrees. And I know this already today, that I may be forced by the learning into an inconsistent situation. And this is a very nasty problem. This is not addressed in most of the policy proposals that are also distributed now in Cancun. So, and that's, yes, thanks. This is one of the problems, especially since the accumulated amount that we are allowed to emit can be scaled by this very simple formula. I'm a big fan of the work on the budget approach in 2009, published in Nature. But here is a paper that does it analytically. This is an analytic explanation, at least it absorbs the analytical ideas from other papers and gives a very beautiful formula on the budget that is allowed given a certain climate sensitivity and the temperature target. And this is a very helpful formula in my view and should be acknowledged much more. So this shows that if climate sensitivity goes to very large numbers, the cumulative amount that is still allowed goes to zero, of course. Yeah. So we cannot fulfill the requirement that we have to prepare for these extreme events. There's another very nasty effect. If you can show under this decision framework, there might be, in fact, and this is a very generic phenomenon, there is no incentive to learn. Yeah? If I already know before, I may learn such a bad thing, I don't want to learn at all. And the natural idea would be that any further information is welcome for a so-called social planner, a benevolent optimizer. And you can show in the standard cost-benefit framework that we condemned at PIC for a very long time, that this is not a big deal because the damages are brought in and you always have a benefit from additional information. It's good to have science, in short. Yeah? But here in this cost-effectiveness analysis, this is not the case. So the fact that you learn more is not really acknowledged. And there are even nastier problems I cannot explain now. So here's, once learning gets in, this cost-effectiveness analysis has a logical defect. And therefore, we think we have to go for a hybrid approach on a very conceptual level. This is not clear at the moment. And we made a suggestion, so there's an overview table we have in the slides on the pros and cons of the different, I've gone through these in essence, you have them in the slides on the web afterwards. So this is one suggestion that works. So you still have the mitigation losses only, no damage function, but instead of the damage function, you subtract the probability that you overshoot. And then you have a function where all these difficulties don't show up. The question is now in the policy advice arena whether these probabilities could be elicited. Yeah? At least they should be discussed. So this is a way, not having to monitorize everything. You are free to monitorize the damages that you do know. You can add them here, but on top of that, you can account for tipping points or whatever. So on this very aggregate level. So this is the end of my presentation. I just want to mention that even if the post-Copenhagen process may not converge very soon, this is no reason to say that mitigation wouldn't work for sure, because there's an alternative there's a plan B, if you like, this post-Copenhagen negotiations, the COPs, and this is a coalition-forming process. So trading systems that do already exist or are planned, they could link together, could be linked to a coalition, a climate coalition, the coalition of the willing in a sense. It's also now a matter of actual research to demonstrate under which conditions such a coalition is economically stable. It's very clear if you have a tough target and you have to compete against countries that produce in a very dirty manner, then it's not trivial that you survive. So we have calculated that Europe is front-running for 10 years. It has an economic benefit because it builds right away the right energy parks, yeah, that are clean, and then if you then get a global treaty, you are fine. You have done the right thing from the beginning. But the question is, how much front-running can we afford? So if it's 60 years, it's not so clear. So therefore, it's good to have this economic analysis at the side, also for coalitions, and then we have to talk about border tax adjustments to compensate the carbon price at the borders. On the other hand, for club goods, that you have technology protocols, you share certain knowledge on non-mitigation technologies only among the club members. Of course, we do not keep the mitigation technology secret if we want to implement mitigation. We want to spread them as much as possible. But we could enact this on the non-mitigation technologies, just on consumption technologies, on consumption goods. So, in summary, the costs seem to be low for mitigation. the inclusion of uncertainty under this cost-effectiveness framework leads to a much earlier investment into clean technologies. We think, nevertheless, that this approach is a bit ill-posed once learning is allowed for, and we need a modified approach, a hybrid approach, out of cost-benefit and cost-effectiveness analysis. And if you have to hybrid with cost-benefit analysis, you have to work with damages. So here comes all the damage and the impact and adaptation community in again, yeah? So chopping off mitigation completely from the rest of the discussion is ill-posed. And my personal hypotheses are that it's very useful to have this economically, in a sense, very, very stylized analysis before the stakeholder dialogue. So this morning we heard, and I fully comply with this, that cost-benefit is very difficult and it's not what applies for adaptation in its pure form, and that it should be replaced maybe by stakeholder dialogues. But I think stakeholder dialogues are facing an amount of complexity that is too large if they are not prepared by model runs, and also not by economic model runs enlarged by this decision analytical aspect. And I think it's good to have some stylized approaches first, and then go into this dialogue, and then maybe refine this analysis. And on the other hand, you have here a tool which values science, yeah, in very explicit forms, and you can point politicians to those areas of science that are underfunded. Thanks a lot.
Thank you, Hermann. I'm sure David Cameron would be very pleased to see social happiness formally recognised inside a time integral. Any questions for Hermann? Yes.
Yes, I wanted to ask you about your optimization under uncertainty bit. So it seems that some of the biggest uncertainties in the whole decision-making process in the 5-year windows are ignored under this scheme, i.e. that the temperature that comes out of the little climate model in the integrated assessment bit isn't actually a real temperature. And what would happen at each stage as the agent goes through the model would be he would see his climate model and then he would actually see the real temperature, and there's uncertainty on that. So there's sort of two big uncertainties at each stage that you have to take account of to do the optimization properly. And what I wondered was, are you thinking about that, and are you working on ways of sort of building those fairly first order uncertainties into your modeling approach?
Yeah, thanks. Once we move into this this new sort of hybrid approach, where we have to talk about damages in some way, then once you talk about damages, of course, all this volatility in temperature comes in. Here we didn't need it because we did not talk about damages at all. We just took the 2-degree target of the European Commission and asked what does it mean in economic terms? What does it cost, and where do we have to invest to comply with it? Once you have to talk about damages, if I'm not saying you have to monetarize, but you have to mirror them in some way at least, you have to deal with this variance in temperature, and then we would add this to this smooth increase we have in this very simple energy balance model, of course.
So in fact, the optimization is for optimizing, making sure that the model temperature never goes above 2 degrees.
Yes, yes.
Not the real climate.
Yes, but this is the way the temperature target is always interpreted. This is the common understanding of any temperature target we have seen so far.
Michael, at the back.
So can I ask, when we have climate models now, we tend to think about the difference between the climate model and the climate, and think about the structural discrepancy. Do you have a similar notion of the difference between your economic model and the economy? And does that feature in your analysis?
Yeah, that's a very delicate point, of course. I personally think that an economic model is not too different from any other of these models that model a complex or mimic a complex system. So anything what you said for climate applies here as well, and I think it would be an interesting exercise to take such a model ensemble of economic models and to apply one of the techniques that you developed. Unfortunately, these economic models don't have the tradition yet, for example, to go for excessive hindcasting. What they do, in fact, is that they try to mimic qualitative features of the economic growth that have been observed. And one do better and others don't. But it's not so easy to write down a likelihood function overnight for these models. This is a big task. It has been now required by within a project that PIC has won under the pressure of the Commission. So this is, I think this is high time that we also go for this validation step, or this likelihood step, if you like.
So I'm just going to come at this from a different angle, actually, which is that I see these stylized models, as indeed I see climate simulators, as tools to help us to form our own judgments about complex systems. And those judgments, of course, incredibly nuanced and depending upon many things that we can't necessarily elaborate on explicitly, but which reflect the experience that we develop as experts in our subject. So rather than having to build in or wedge in a likelihood-based framework to account for model structural uncertainty and so on, I wonder if instead that you would feel comfortable on the basis of all the experiments that you've done with your stylized model in making a personal statement about what you think the costs of meeting a 2-degree target are. Do you feel that you could sign your name to say not more than 2% of GDP on the basis of the experiments?
Yeah, that's a very interesting question, also from the point of view that in the end the authors of the IPCC will have to do this, or will have to answer this question. And I personally would like to wait for a more elaborate investigation of the past with these models. But my bet would be that in fact I could sign it. So there have been so many sensitivity studies done, there are other workshops on this, that I have the impression it's a quite robust effect. What is not so clear whether the societal frictions that occur if you really want to implement these new technologies on a massive basis, if these are factored in. They are not mirrored here, of course, yeah. But this is a different question, of course. So for these economic numbers, yeah, I personally would be very surprised if the costs were much larger than 2%.
Okay, if that's all of the questions, I suggest we take a short break before the end of the discussion session. Shall we say 20 past? And should we just thank Hermann once again for a very interesting talk.